In this video, we explore the skills a student might develop by engaging with data in science, and we explore the potential for developing a deep understanding of the importance of interpreting data as evidence through working with real-world data. Collecting and analysing data, whether from primary or secondary sources, are skills that students will develop over time, which will help them understand how science works, as well as helping them to make sense of the natural phenomena of the world around them. Graphs are used as visual representations of data, and graph skills are cross-curricular and transferable. There is an opportunity to develop understanding while connecting the scientific context of graph use with cross-curricular skill development that helps make science relevant for all learners and is inclusive of all learners as they engage with science in their everyday lives. Through engaging with data in science, students will move from simply identifying data to developing skills of analysing and interpreting data as evidence to support an opinion, as well as identifying anomalous observations and drawing and justifying conclusions. This development is described in the Learning Outcome Nature of Science 4 in the Junior Cycle Science specification. As students engage with graphs, they might come to understand that graphs are a way to visually illustrate relationships in the data. The purpose of a graph is to present data that are too numerous or complicated to be described adequately in text. A graph is useful if the data shows pronounced trends or reveals relations between variables. If the data doesn't show any significant trend, this can be described in the text. Through engagement with graphs, students might be supported in developing their understanding of both quality and purpose. For example, a basic requirement for graph is that it is clear and readable. For most purposes, the vertical axis or y-axis represents the dependent variable, and the horizontal axis or x-axis represents the independent variable. For example, time is often an independent variable and is usually on the x-axis, as seen in this graph. Consideration should also be given to the scale used, both when creating and interpreting graphs. It is important to consider what is the best way to represent your data, and to consider the kind of data to be presented. If the independent and dependent variables are both numeric, a line graph is visually more useful. If only the dependent variable is numeric, a bar chart can give a clearer representation. And for proportions, a pie chart can convey this type of information more easily. Noticing patterns and relationships in graphs helps with data analysis to interpret data as evidence in science. Patterns in graphs include the overall shape of the graph, noticing what the graph is doing when reading from left to right, if it is increasing or decreasing or plateauing, and relating this to the data. Mathematical calculations for the slope and other calculations or features such as the line of best fit can also be used to explain changes in the data related to the shape of the graph. Relationships in graphs that have particular significance in science are linear correlations, as either proportional or inversely proportional, and can involve a range of variables such as mass, time, temperature, volume, potential difference, current, resistance, and more. For example, a graph of the variables current and potential difference, also known as voltage, illustrates a positive proportional linear correlation between these variables as seen on the slide. Interpreting the shape of this graph tells me the following about the relationship between these two variables: that an increase in voltage will produce a corresponding increase in current, and that current and voltage are related in a positive way, because when one increases, the other increases. An inversely proportional linear correlation is seen in the graph here, illustrating the relationship between the variables current and resistance. The shape of the graph tells me the following about this relationship. As the resistance increases, the current decreases, provided all other factors are kept constant. The linear correlations in these graphs show relationships that hold for most substances, but in real circuits, resistors like filament light bulbs heat up and increase their resistance as the current flows through the circuit. As resistance increases for a set voltage, the current no longer increases proportionally. A more realistic graph in a real circuit for voltage and current with resistors is shown here. Many biological systems have linear correlations. For example, mass and energy conversion from metabolic activity in living things also have a proportional linear relationship, shown here in scatter plot 3 graph. The same graph relationship is representative of the mass-energy equivalence principle across science. A bell-shaped curve graph is similar to the growth curve of microorganisms in a batch fermentation process used in beer production, for example, is shown in scatterplot 5 graph. And the distinctive exponential curve that represents the human population growth curve, as well as the growth curve for microorganisms with a continuous supply of food, is seen here in scatterplot 2 graph. Earlier we mentioned real-world data. So what do we understand by this term? Real-world data in its broadest sense is data collected from the real world from observations based on what happens organically and reflects the scientific process about how science works and the nature of science. In considering how engagement with real-world data might support students in learning about the nature of science, you might in your department think about the following questions. What's important learning for students about data handling, from working with relatable primary data that students collect themselves to secondary data gathered from reliable websites that have validated methodologies behind them? Is real-world data only from dry science, where lab data is data modelling wet science investigations, or can either be both? How does real-world data differ from data students collect in the lab? And what is important to know about the difference? What does this look like? Can students collect their own real-world data? Does engaging with real-world data help students experience the nature of science differently, and why? How does real-world data help with understanding the nature of science for example, in terms of developing a scientific habit of mind about how science works? These are some questions that can help scaffold students' learning about data and science, and the development of analytical skills to interpret data as evidence, to identify anomalous observations, all of which can be used to support findings and opinions. What else is important about data and graphs? In this TED-Ed short video, Leah Gaslowitz shares some things to look out for when using graphs. She explains that when used well, graphs can help us intuitively grasp complex data. Leah also explains that as visual software has enabled more usage of graphs throughout all media, it has also made graphs easier to use in a careless or dishonest way, and that there are plenty of ways graphs can mislead and outright manipulate. Understanding how graphs can be used in misleading or manipulative ways helps identify what is important to know about the use of graphs in communicating in science and beyond. Watch the short video from the QR code on the screen here, or use the YouTube search function. The references used for this screencast are shown on the slide here. Thank you for listening.